So in today's lesson, we're going to be learning about reverse engineering. So taking apart a compiled program or obfuscated one and try to decompile it, see what their contents are. First thing I want to mention is if anybody has any donations they want for the club for snacks or mainly just snacks, honestly, that would be much appreciated because we do have a limited budget and we're going to use that budget for SD cards and for buying some of the snacks, but they're not going to last forever. So review. So some of the reviews I want to do is Linux commands. Anybody know any common Linux commands? What does ls do?
List.
What?
List.
List what?
Directories.
List directories. What does the cd command do?
CD grants permissions? No, that's the chmod.
Yeah, chmod. Chmod grants permissions. What does cd do?
Oh, it puts you in a directory.
Puts you into a specified directory. What does cat do?
What?
C-A-T, cat. Concave.
Reads a file? No.
Reads a file. Yeah, shows the contents of a file. What does anybody know how to actually run a file? What command? What you have to specify? That's for running Python files. What if I had a C file? How would I run that?
You put
Nano.
No,
Okay.
not nano. So to run a file, does anybody remember you have to do // and then the file name?
Oh.
So // file name, and then I'll run the file. Okay, so we're actually going to be using Gehydra today, and that's how we're going to be reversing most of our programs, seeing the contents that isn't actually shown. What's our environment variables?
Directory.
So environment variables aren't stored on directories, they're stored on your local file system. So environment variables are used for doing specified values anywhere inside your system. Last thing, does anybody know what the user prints out? The echo command. Does anybody remember the echo command?
Yeah.
Yeah, so echo $user, and now print out to your terminal.
It'll be your user.
And what does everyone get? So Cal user, right? Perfect, okay. Last thing before we get into our lesson, which is going to be the main basis of our lesson, is C, the programming language C, secure? No, it's not. So the reason why we're going to be learning more about reverse engineering and the reason for learning C is because it's not secure and you're able to decompile it to find some vulnerabilities or to actually allocate in memory to get to specific points of the program that you're not able to get to. More about that later. So a few things before we get into that. We're going to talk about some characters and running some neovim commands. So the first character I want to talk about is the wildcard, the asterisk symbol. So this wildcard symbol is used for auto-completing files that you're wanting to list. So let's say it's kind of like the tab button. So if I were to do ls and I wanted to specify the file buffer, press tab, and I'll complete some lists. So the asterisk symbol will auto-complete all that. So if I were to if I were to do list, right, buffer, and then do the asterisk symbol, it will auto-complete what is available, buffer overflow cyber and buffer overflow cyber.c. And that's just an easy way that you can put inside programs to actually auto-complete. And in some instances, when we get later down in the road, when we're going to talk about web security and stuff like that, you're going to be using asterisks to auto-complete these kinds of things. Okay, another thing I want to talk about is the neovim commands. So everybody pull up neovim. And some commands we want to run on neovim to make sure that we have everything installed and it's updated is Mason. Everybody type in the terminal at the bottom, :Mason. Okay, and does everybody see this install header right here? It says installed. For you, Brayden, go all the way to the bottom until you get to the T section in the alphabet. And it should say TypeScript, language server, and...
No more TypeScript. No.
Yeah, it's only going to be necessary so we can get some of the coloring and functionalities available. We're not actually going to be programming in TypeScript.
Thank you.
go back to your terminal and type in the command sudo apt get install npm. Okay, how about everybody else? Let's type in some things that we're going to need to learn for nvim. Everybody type in Control N, and well, if you still have this menu popped up, press Q to exit it. And type in Control N, and right now you're going to it's going to show all these directories and all these files that you can go to. You can use your mouse or your keypad and press Enter to go to different files. So right now, if I go to downloads, press Enter, and I go to snake.py, and I press Enter on the file, you can see that it opens up the file and everything inside that file. And then to exit out, you press Q. Another thing we can also do in NeoVim is press space twice. So if I press space twice, it will show the list of these files and things that I can do inside your current directory and your recent ones.
I'm back in NeoVim.
Press Q again, or yeah, press escape Q, or tab. There we go. Press escape. There's an escape key to exit out of that one. Last command we're going to want to do is run packer sync. All right, just make sure that everything's up and running and updated. Okay, so with this lesson, with reverse engineering, we're going to have to be learning about file types and some local addresses. So the first file type we're going to want to know about in the basic one used for Linux is the executable and linkable format, or otherwise known as ELF, which is the standard binary format for operating systems like Linux. So everybody go into your terminal, or at least I'm going to go into my terminal really quick, and I'm going to run the command file buffer overflow-c, and that's going to tell me what this file is. So as you can see, it's an ELF at 64-bit. LSB stands for least significant byte, which we'll talk about more later. We can also see that it can run on x86 and x64 systems. It's dynamically linked, and what its interpreter is, so how it can run, and if it's stripped or not, which we'll explain later. We can also run that command on other files like buffer overflow-c, and we can see that it's a C file that was running CASSCII. Of course, the executable link, most significant bytes. Okay, so what was shown here, if we were to run this command again, not that one. Not fudge. Okay, if we can run here, we can see LSB. So LSB stands for least significant bytes, and what that means, it's showing from the most significant bytes on the left side of its partitions, and the least significant bytes are on its right side of the whole partitions. Let's look at a diagram. This explains it a lot better. So we have this address, this binary address here, which is, specifying some values. And we can see on the left side is where the data is stored for its most significant bytes. And on the right side, the least significant bytes. So that's just how it's ordered, how it's represented. If we said, for instance, that at byte 1 on the left side represented, the value 1, then that would represent that value 1. But of course, if we're using most significant bytes, it's going to be different. Okay, here, I got an idea.
So it doesn't really matter what the number is, it just matters the placement of it?
It actually does matter what type it is, whether it's least significant or most significant.
No, it doesn't matter if it's a 1 or a 0.
Oh no, it does matter whether it's a 1 or a 0, if that's what you're saying.
Mm-hmm.
Okay, let's say for instance, we have this binary here. Okay, so we have this symbol right here, this byte. And let's say this byte is equal to 128. And by the way, I'm using most significant bytes right here. Okay, So now if we were to look at this one, it will be something like something lower than 128. So let's say like 64, and so on and so forth. It will go increasingly lower because the most significant bytes, the most significant value, is here at the front, while the least significant will be here at the right side. So that's how you can differentiate between those two. Okay.
So we can't physically tell what is the most significant byte.
Well, let's say for instance, you were to dump your addresses for a file. So if I were to run the command, whoops, yeah, you're right. So if I were to run the command hex dump buffer overflow -c, we can see that the addresses on the left side are dumped and the values on the right side. So if I went to value here, right, we can see that this value corresponds to that value, which is .elf. But this one is more complicated to read because it's compiled, and you can actually see these empty spaces. These dots all over here are empty spaces. So let's say if I were to run hex dump on the .c file, boom, now we can actually see the import, right, our actual commands, our functions, our variables and strings, and their specified value, which is shown here. Okay, so next thing is we want to talk about is binary. I think most of you guys know what binary is. It's a number scheme that represents data in digits with two numbers, ones or zeros. And the thing about binary is that it increases in its value. So I'm going to pull this up again on the whiteboard. How do I delete all this? Does anybody know?
You go to the little square with the eraser.
Nice, okay. So let's say I have this right here. This represented is 1 byte. So it will be byte. What? Oh. So this will be represented at byte 1 with the exponential value of 1. This will be byte 0 or byte x with the exponential value 2, and it goes on so on and so forth. So with this, it kind of gets a little bit math technical. The more bytes, the more values you add over here, the greater your size is going to be. So right now, if anyone were to pull up their calculator and were to do like 2 to the first times 2 to the second times 2 to the third, right? You see that eventually it'll get to some certain value. So okay, so this is actually representing the first value, right? So this placeholder right here can represent a maximum value of 2 bytes. This placeholder here, okay, let's do a different color. This placeholder here can represent a max value of 4 bytes. And then this one here can represent a value of 8 bytes, and so on and so forth until we get to a really high exponential value. But that's how memory is stored, right? It's stored in these bytes, and the more incremental values to it, the higher the storage is, you can say. So we can even see at the bottom, right? 2 to the first is what was that? Oh, 2 to the 0. Okay, I made a mistake. So in the first part, it'll be 2 to the 0th, which...
That's what I was trying to say.
So 2 to the 0th is equal to 1, if everybody remembers the math, right? And then 2 to the first, it'll be 2, and then 4 bytes. So 4 bytes, 8 bytes, 16 bytes, 32 bytes, 64 bytes, 128 bytes is stored in that, is how much you can store in that system right there. So if everybody were to pull up how many bytes one character is, like if anybody wanted to know how many bytes the letter A stores, it would say that the letter A stores this many bytes. I don't know how many it stores, but that's how you can say in that, right? And that's how many bytes you can add to it. And eventually we're going to need to actually know how many bytes certain characters can add to a value so we can't allocate memory. We'll talk about that a little later. Okay. Next thing is hexadecimal or hex values. So hexadecimal is a numbering scheme like binary that ranges from the value 0 to 9 from A to F. A good way to represent this is through with the binary again, but with hex values. So let's say I have the binary 0, 1, which is byte 1. Well, that's equal to the hex value of 0x01. And that's how you represent hex values, by the x values of that. Okay, so let's say now I have the binary of 1, 0. Well, that's equal to the hex value of 0x02. Oh, geez. Well, that's a 2 right there, not a 3. Okay, and this increments over and over until it gets to the value 9. And when it gets to the value 9, it transitions to the letter A. And when it transitions from the letter A, from these values, it will go from A to B to C to D to F. And once it transitions to F, then the placeholder goes on to this second value. Going back to our file system in the terminal, and we were to hex dump our file, you can see that it's represented by hex values of where that value is stored.
It'd just be A6.
Okay, so obviously it can be represented as 0xA6 or just A6.
Okay.
It doesn't actually matter, but the 0x in front of it is going to tell you, hey, it's a hex value. All right, but when you have it at A6, you might not realize it at first, unless you see a pattern going on, or if you know that that hex value is part of the whole memory.
Okay.
Okay. Hex values are going to be pretty important to actually know and memorize. Okay, not memorize, just to know, because we're going to be dealing with memory allocation and we're going to need to know specific addresses of hex values. The next value we're going to need to learn about is decimal values. So decimal values is another way to represent data and digits, but it's much better than binary or hexadecimals, because we're actually using the decimal format. So to represent data using hexadecimal, let's say I have the value 1, and I want to represent that in decimal. Well, to represent that, the value will be 1. If I wanted to represent 2, the value will be 2. If I wanted to represent 3, the value would be 3. What would the value be if it was 4? 4, okay. So that's how you can represent data using decimal. Now alright, the next thing we're going to learn about is addresses in programming, or in programming files for storage and memory allocation. So an address is where in the program data is stored. And the way we can actually represent this is, again, through the hex dump command. So we can see here that in this section and this section is where the address is stored for the data in this section. So at address 0 here, we can see that it is that value for that section. And eventually we're going to have to learn about addresses for where each memory is stored inside each address. Now if everybody were to look at that chart over at the right side, can everybody see that?
Yeah.
Can you see that, Braden, in the back? Here, I'll draw it instead. Okay, let's say we have this data set here, and it's split into 4 columns. It's represented by 0, 0, right? 0, 1, 0, or actually 1, 0, and then 1, 1, right? Does anybody remember how much storage you can have in a 2-byte binary? 4, yes. So obviously we accounted all of our storage sets and we can only use 4. So of course, again, correlation. So we can assume that at address, at address 0, 0, the value 1 is stored. At address 0, 1, value 2, 3, and 4. We could just assume that for now. And the address is where that value is stored. Now, what address is the value 4 stored in?
1, 1.
Yes, binary 1, 1. Where is the address for 1?
0,
0,
0.
0. Okay. So that is obviously where it's stored inside our memory, inside our files for our programs. 0, 0 is stored for, 1 is stored for at the address 0, 0, and 4 is stored at the address 1, 1. Now that's just a simplified version. It gets way bigger than that, but that's how you can see where that is. So obviously this chart here is a way to represent binary, decimal, and hexadecimal in a correlation. So here we have the binary 0, the decimal 0, and the hexadecimal, jeez, mouthful, of the value 0. And then obviously as we go higher and higher, the binary 1 represents decimal 1, hexadecimal 1, and so on and so forth until we get to binary 1001. But then if we go over here, we can see that it's also transitioning for hexadecimal to letter A, right? And then B, C, D, E, F, blah, blah, blah. There's a tool that I actually want to show you guys. You guys, Sam, you remember CyberChef?
Yeah.
All right, so CyberChef is actually a really cool tool to transition binary or hexadecimal values to actual readable values. So of course, if I had the binary if I had this binary, and if I were to transport it into the input, it will, and if I had these functions over here, and it said from binary, right, I type in from, or type in just binary, you can see this option from binary. I can put that in there, and it will transition the binary
Is that
to
stuff from the...
yes, this is from the presentation.
Right, I'm gonna...
Now, if I were to do this from binary, I would get this output. Now, there's a reason why you get this output, and it has to do with the byte length. So how long of the length is this binary right now? You can see that it equals to 7, right? 7, because if we were to look at this, let's say 1, 2, 3, 4, 5, 6, 7. That's how long the byte length is between each space. So if we did the byte length 7, the output would be CyberElites. Just a fun little thing. It's always been there for each presentation we've had. Next thing we're going to learn about is assembly. Assembly is the process for internal computer processing for the internal computer processing unit, also known as a CPU, to execute and manipulate program addresses. And usually with assembly, it's categorized by these commands. And I'll show you these commands with this PDF. So these commands are set over at the left. We have the move command, the SDC, all of these. These are an entire list of all the commands assembly uses. And they use these commands to manipulate the addresses on a computer program. So for instance, if you want to move a byte, or in this case is destination or source, to another part of your program, that's what that's for. You can also use the push assembly command, which pushes a destination or a address to another part of your program. So we're not going to actually be learning about all of these because this gets a little complicated, and there's a whole lot. I mean, there's a lot that you have to learn here. But usually, even when I disassemble a program, I don't usually look at the whole assembly unless it's something really obfuscated, in which case then I would look at the assembly to know what's going on, in the program. All right, the next thing we're going to have to learn about is the CPU registries. So these registries are used to They're the accessible points in your program. So let's say you have two addresses in your program. These two addresses, you can think of it as address 1 and address 2. To the whiteboard real quick. So I have this address here, and I have this address here. I'm going to call this one like ADD1 and like ADD2. And a point and the registry is used to connect these two and have them go back and forth. And usually we can specify a registry with the jump assembly command. And that's how they're able to go back and forth or just go to one straight point. So you can have it go one way or you can have it go both ways. Alright, next thing are pointers. So pointers are a way to store your data inside a program and to use it like at a later point in your program. So if I had a pointer and I had the value of some address, right? I can use that specific address to call it onto a later point. So the reason why pointers are a thing is that when you're programming, if you weren't to use pointers, you can't actually manipulate the whole assembly, the whole addresses of the entire program, right? It's just going to be these functions, these variables, but you can't actually manipulate the entire program. But with pointers, you can actually do what you want with those programs. So one thing I want to do with pointers and to actually demonstrate them more on this scale is I'm going to run the command gbd and then buffer overflow. So I'm going to run this command gbd gdb and it's going to basically go from each point inside the file and some stopping points inside that file. So if I were to do if I were to make some breakpoint, like if I were to run this, it would show where in each point that is starting from. So I started the program. It's saying that it's being hosted from this compiler right there. And right now, password is actually inside the program. Here, if I were to actually open this file, or read the contents of the file real quick, we can see that it's going, and at this point, right here, it's asking for user input. So it's saying password, and right now we're at the section password, as below here. So if I were to just type something, right, denied, and it tells you where it exited and stuff like that. So I'm going to do a command disable main, and what that's going to do is, what that's going to do is that's going to set a breakpoint for the function main. And if you guys remember, in every C function, there comes the main function. You have to have a main function in the C function. I mean, technically you can have C program without the main function, but as most times you're going to have the main function. So I have the breakpoint main, and if I were to run this program again using the run command down below, you see here, it's going to run it, type something, and same thing. Okay, so what I'm going to do is I'm going to make a breakpoint for the main function, and then I want to analyze the function. So the analyzing the function is going to take each registry, each pointer from our program, and it's going to go basically each registry at a time. So we're going to run gdb buffer overflow, right? And we have to specify some breakpoints in our functions. So I'm going to disable main, and that makes it so that we can actually make a breakpoint on the main function. Then I'm going to do break, and then remember, we gotta do a pointer to specify the address of our function. So we do pointer at the address main, and that shows where our address is, which is 0x1169. And then now what we're wanting to do is we also want to look at our registries for this program. So I'm going to type in registers. Okay, so run it, right? Then enter your registries, info registries. And right now what is shown is it's talking about all the, the assembly commands here at the left and what kind of addresses are being shown here. So if we were to run this, if we were to run it line by line, it's going to do this address. Then it's going to do that address, and it keeps going all the way to the bottom. So let's run this, and we'll start from the beginning, and we can see at breakpoint 1, it has it at that address. If we enter again, or run it again, yes. Oh, run the command ni to do it address by address. So we run the command ni, then it has address 16a. Run the command 16d, 171 at the far right, 178, 17f, keeps going, right? So it's setting probably all those variables and setting up our program. And now we're at the registry where it asked for a password. So if we were to go back real quick at the terminal and we read the contents of the file, do you guys remember where it's specified for our password here? Mm-hmm. And when we go to our program where we're disassembling it, we can see that at address that at the end 198, it's now asking for a password, right? So just enter whatever, keeps going. So it says that 1960 keeps going. So it's probably checking it right now. It checked it. Now it's denied at address 1C6, and it keeps going until it exits. There we go. So with this, this is a small breakthrough for running each command, for running the program slowly, right? Because if I were to just run this command right now, it'll ask everything instantaneously, password, and then whether the password is correct or not. With this, we're able to see what is happening at each address. Next thing I want to do is the buffer overflow for this program. So with this program, the reason why I call it buffer overflow is because there's a buffer overflow for the program, for that program there. Now, does anybody know what a buffer overflow is? So what I was mentioning there before is that there's a data set between a few addresses, and a buffer overflow is where you allocate enough memory to go to a different address. So let's say I'm at address 0x03 and the max amount of storage is 4 bytes. Then I add another byte to get to that fourth address, and then I could add another byte to go to a different address, which is to the place that you want to be at, even though you're not meant to actually go there. That's the vulnerability, that's the exploit. So in this case, we can actually see that there's a reason why this vulnerability exists for this program in particular. So with this, we're getting the user input of 6 characters, 6 bytes long. And then in here, we're comparing the user's input with the password. If the user's input is the password, then we get, well, actually it's comparing whether it's not. So if it's not, if it turns true for it being not, then it will say denied, else if it is true, then it'll be granted. And then if we get granted access, it has this authentication to 1. And you guys remember what 1 represented for Booleans?
True.
True. And what does 0 represent for Boolean?
False.
False. So if 1, which is true, then we get printed to the system's files and stuff like that. And then we exit the program. But there's a reason why this has a vulnerability. One is because we have a limited set amount of characters, a limit amount of bytes, which is 16. If we were to go over 16 bytes, that's when we get the buffer overflow. So we can see at this function, or this method gets, it gets the bytes of user input, which it doesn't check. It doesn't check whether 16 bytes has, over index where we've gone over 16 bytes. It just says, okay, we have this many bytes. Now I'm going to do my functions. And that's the vulnerability right there. Okay. So if I were to run the file buffer overflow -c, whoops, /, it'll ask for the password, of course, right? I type in the password, or what I think the password is, right? And then it says we get denied. But if I were to just allocate memory, remember how many characters were we able to put? 16 bytes. So if I were to over-index our bytes by, let's say, that much, boom. Now, even though it says access is denied, we were to allocate to the point where access was granted. So it says, boom, you gained access into the system. So that's how we did a buffer overflow to get to a point in the program where we weren't supposed to go into. Okay, let's see, what's next? So one last thing before we go on to our challenge for today is radar. Radar 2 specifically is a more advanced way of using Gehydra and using that GDB program, where we're able to see each address and each registry in order of how it's executed. So let's say if I were to do radar 2 and then buffer overflow -c, boom, now we can see these addresses. I haven't really used radar 2 that much, so I don't really know how to use all the commands in it, but radar 2 is really, really helpful. Oh, geez. So I'm going to exit out of that really quick, and we'll use radar 2 later on throughout our...
I don't even have it.
Yeah, you might have to install it, but I'll hold off for that for now. Once we get our SD cards, then we can install some programs.
Okay.
Right now, you guys are probably on the limit of how much storage you guys have. Okay, now we're going to do our challenge. Now you guys should see the repository. Just input that URL. Now you should see the repository Cyber Challenge October 14th. Today we're going to be doing the C program challenge over here, right here, over at this file. Click on C program challenge.
Okay.
Oh, whoops, I'm doing that. Okay.
Blame.
And what you want to do is, you see raw, view raw right there?
Yeah,
You're going to want to press that. Work. Now everybody, before we do nvim on that, we want to go to our downloads real quick. Type in ls. And does anybody remember what the command was to see what a file is? To see the type of that file, we'll use the command file. Okay, so the file command, of course, shows what kind of file your file you specified is. So it's ELF, 64-bit, least significant byte, and can run on x86 and x64 operating systems. So if you were to read the contents of C program challenge, you might see that, oh look, it's compiled. We're getting random values where we're not able to see the actual values of our program. Does anybody remember what software is used to decompile the system? Gehydra. Okay, so everybody run Gehydra. All right. So what we want to do is we want to do a new project. Hit next, and project name just do cyber or whatever you want to specify it.
Loser project.
In that, you want to do import file, and then go to the file where C program is stored. So C program is stored in my downloads. I'll do select file to import, and then let that file import. And right now you're going to see that its format is ELF, right? Its language is the default GCC, which is our compiler. And then we have our destination folder and our program's name. Now, GCC was our compiler, remember?
Oh yeah.
Made by GNU.
Yeah. I asked that question. I remember that.
Yes. So the GCC compiler is how our program was compiled and how Gehydra is going to decompile that program. So now you want to double click on C Program Challenge. So double click on that or press enter if you're on keyboard. Now is when I want you to analyze it. You're going to hit yes. You want to always analyze it. And there's a lot of options that you can have for analyzing this. We're not going to get into it. Don't enable or disable any of them. Just hit analyze. Keep the defaults. It's always good to keep the defaults.